In 1948, a physicist working at a light bulb factory in occupied Holland proved, in a paper barely 3 pages long, that empty space is not empty. He showed that 2 metal plates, uncharged, placed in a perfect vacuum with absolutely nothing between them, would be pushed together by a force, not gravity, not magnetism, a force generated by emptiness itself. And that same year, on the other side of the world, 3 of the most brilliant physicists alive did something stranger still. They found the energy of that emptiness sitting in their equations, looked at how impossibly large it was, and erased it. They set it to 0. They wrote it out of physics entirely. Their reward was the most accurate scientific theory ever built. The number they deleted sat quietly for 50 years, and then it came back, as the worst prediction in the history of science, and as the force now pulling the most distant galaxies in the universe beyond our reach forever. So what really happens when physics finds an answer too disturbing to keep? Get comfortable and settle in. Subscribe if you have not already, and stay with us tonight, because the thing physics erased is still written into the empty space all around you, and by the end of this journey you will understand exactly what it says. Let's get into it. Part 1. The force from nothing. There is an experiment you can run, and it has been run many times in laboratories around the world, and it produces a result that should not be possible. You take 2 metal plates. They are ordinary plates, flat, polished, uncharged. You place them facing each other inside a vacuum chamber. Then you pump out the chamber. You remove the air, and then you remove what is left after the air, until there is nothing between those 2 plates at all. No gas, no dust, no light, no radiation of any kind. You have built between those 2 flat pieces of metal the closest thing a human being can construct to a perfect nothing, and then you watch what the nothing does. It pushes the plates together, not gravity. The plates are far too small for their own gravity to matter. Not static electricity, not magnetism, not any leftover charge, because the plates are uncharged, and the experiment is designed specifically to rule those things out. The plates are drawn toward each other by the empty space between them. The nothing has a force, and if you bring the plates close enough, that force becomes enormous. At a separation of about 10 nanometers, which is roughly the width of a few dozen atoms laid side by side, the pressure that the emptiness exerts on those plates reaches about 1 atmosphere. That is the same pressure as the entire weight of the air above your head, the whole column of atmosphere stretching from where you're sitting all the way up to the edge of space, pressing down on every square centimetre of you right now. Empty space, with absolutely nothing in it, can generate that. I want you to sit with how strange that is, because we are going to spend the next 2 hours unpacking it, and the strangeness only deepens. We have a word, nothing, and we use it casually. We say there is nothing in the box, nothing in the room, nothing out there in the dark between the stars, and we mean it as an absence. We mean that whatever could be there simply is not. But the experiment with the 2 plates is telling us that this is wrong. It is telling us that nothing is not an absence. Nothing is a thing. It has properties. It has energy. It has a pressure. And under the right conditions, it will reach out and move solid objects. Take a moment before we go any further and think about how deeply the ordinary idea of nothing is woven into the way you picture the world. When you imagine the space between the Earth and the Moon, you imagine a void, a gap, a stretch of pure absence that light happens to cross. When you imagine the inside of an atom, which is by volume almost entirely empty, you imagine a tiny hard nucleus and a few electrons, and around them, nothing at all. When you imagine the vast dark distances between the stars, the light years of black that separate one sun from the next, you imagine emptiness, the truest emptiness there is. And in every one of those pictures, nothing is doing the same job. It is the stage. It is the inert backdrop against which the interesting things, the matter, the light, the energy, play out their drama. The stage itself does nothing. The stage has no lines. That is what a stage is for. What the Casimir experiment quietly destroys is the idea of the stage. It says the backdrop is not inert. It says the emptiness between the stars, the emptiness inside the atom, the emptiness in the gap between 2 metal plates, is itself a participant in the drama. It carries energy. It exerts pressure. It is, in its own restless way, alive. And if that is true, If the nothing is not a stage but an actor, then a great many things you thought you understood about the universe are standing on a foundation that is not what you assumed it was. That is why this story is worth your evening. It is not a story about an obscure little force in a vacuum chamber. It is a story about discovering that the most basic ingredient of reality, the thing we call empty space, the thing we thought was simply the absence of everything else, was hiding a secret all along. This is not a fringe idea. It is not speculation, and it is not one of those theories that lives only on the chalkboard and has never been tested. The force I am describing was predicted in 1948 by a single physicist in a paper that was barely 3 pages long. It was confirmed in the laboratory to a precision of about 1% 50 years later. It has a name. It is called the Casimir effect, after the man who predicted it, and it sits today as one of the most quietly unsettling results in all of physics. Because the force itself is only the beginning. The force is the doorway. What lies on the other side of that doorway is a story about how physics found the answer to one of the deepest questions it has ever asked, looked at that answer, decided the answer was unusable, erased it, and then built the most successful scientific theory in human history on top of the erasure. The question is simple. What is empty space? What is the energy of nothing? And the reason this story matters, the reason it is worth 2 hours of your attention tonight, is that physics already solved it. The answer was worked out more than 60 years ago. It is sitting right there in the equations that run your phone and your computer, and every piece of modern electronics you have ever touched. And then that answer was struck out, set to 0, written out of the textbooks, because when physicists looked at what their own mathematics was telling them about the energy of empty space, the number was so catastrophically wrong, so impossibly, world-endingly large, that the only thing they could think to do was pretend they had never seen it. But you cannot really erase something that is true. You can stop talking about it. You can leave it out of the lectures. You can teach 3 generations of physicists a tidier version of the story. But the thing itself does not go away. And the energy of empty space did not go away. It sat there, quietly, for half a century, and then it came back. When it came back, it produced what is, by a wide and almost comical margin, the worst prediction in the history of science. And it turned out to be the same thing that is, at this very moment, pulling the most distant galaxies in the universe away from us, faster and faster, toward a darkness from which their light will never return. That is where we are going tonight. We are going to start with 2 metal plates and a man in a light bulb factory, and we are going to end with the slow, silent closing of the entire sky. So let me take you back to the beginning, to the question itself, because before anyone could erase the answer, somebody first had to discover that empty space had an answer to give, and that discovery did not come from someone who went looking for it. It came from a number that a very reluctant physicist found in his equations, a number that would not leave, no matter how much he wanted it gone. Part 2. The restlessness that cannot be removed. The story of the energy of nothing does not begin with the man who built the 2 plates. It begins 37 years earlier, in 1911, with a physicist who did not want to find what he found. His name was Max Planck, and he is, by any reasonable accounting, one of the founders of the entire modern world. It was Planck who, in 1900, had cracked open the problem of how hot objects glow, and in cracking it open had accidentally launched quantum mechanics. He was not a revolutionary by temperament. He was careful, conservative, a little reluctant about the strange new physics he had set loose, and in 1911, working on a refinement of his earlier ideas, in what became known as his second quantum theory, he ran into something that made him deeply uncomfortable. There was a term in his equations, a small one. It can be written as 1/2 h nu, where h is the constant that now bears Planck's own name and nu is a frequency. And this term refused to go away. It appeared in the energy of every oscillator in his model. Now, an oscillator in this context is just anything that vibrates, anything that can hold energy by moving back and forth. And what Planck's mathematics was telling him was that every one of these oscillators, even when you cooled it down as far as it could possibly go, even when you took away every last scrap of heat, still had energy left in it. 1/2 h nu of energy. Energy that could not be removed. Energy that was simply there, for no reason that experience could explain, because the mathematics demanded it. Think about what that means. Absolute 0 is the coldest temperature there is. It is not a temperature you can go below. It is the floor of all temperature, the point at which, in the old classical picture of physics, everything stops, all motion ceases, every vibration falls still. And Planck's equations were saying, no, even there, even at the absolute bottom, the oscillators are not still. They still carry energy. The stillness that we imagine, the perfect quiet of a thing cooled to absolute zero, does not exist. There is a floor to the energy, and the floor is not zero. 2 years later, in 1913, Albert Einstein, working with a physicist named Otto Stern, gave this leftover energy a name. They were studying the way hydrogen gas holds heat at very low temperatures, and they found that the numbers only made sense if this strange floor of energy was real. They called it, in German, Nullpunktsenergie, 0 point energy, the energy at the 0 point, the energy that remains when everything else has been taken away. And here is a detail I love, because it tells you exactly how unwelcome this discovery was. That same November, Einstein wrote a letter to his friend Paul Ehrenfest, and in that letter he declared 0 point energy dead. His actual word in German was Mausetor, stone cold dead, dead as a doornail. Einstein, one of the greatest physicists who has ever lived, looked at this energy that his own work had helped uncover, and his instinct was to bury it. He wanted nothing to do with it. He hoped it would simply turn out to be a mistake, a quirk of the math that would dissolve under closer inspection. It did not dissolve. And the reason it did not dissolve is the most important thing I'm going to tell you in this entire chapter, so I want to lay it out carefully. 0 point energy is not a feature of one particular theory. It is not something you can argue away by choosing a different interpretation or a different set of assumptions. It is a direct, unavoidable consequence of the single most thoroughly tested principle in all of physics, the Heisenberg uncertainty principle. Here is the logic, and it is airtight. The uncertainty principle says that there are certain pairs of properties that you can never know with perfect precision at the same time. The classic pair is position and momentum, which is just a physicist's way of saying where something is and how it is moving. The more precisely you pin down one, the more the other blurs. This is not a statement about the limits of our instruments. It is a statement about the structure of reality. Position and momentum do not both have perfectly definite values at the same time. They cannot. Now imagine a particle sitting at the very bottom of a well, the lowest energy place it can possibly be. If that particle could have exactly 0 energy of motion, it would be perfectly still, and it would be sitting at one perfectly definite location, the bottom of the well. But that would mean you knew both its position and its momentum at the same time with perfect precision. Its position would be the bottom of the well, its momentum would be exactly 0, and the uncertainty principle absolutely forbids that. It is not allowed, so the particle cannot be perfectly still, it cannot sit quietly at the bottom, it must jitter, it must always carry some small, irreducible motion, some minimum energy, because if it ever stopped completely, it would violate the deepest law we know. I want to make this real for you, so close your eyes for a moment, or just let your gaze go soft and imagine that you are that particle. You have been cooled down, every scrap of heat has been drawn out of you. You have been brought to absolute 0, the coldest it is possible to be, and you are asked to do one simple thing. Hold still, just stop moving, settle to the bottom and be at rest, and you find that you cannot. Not because something is pushing you, not because there is heat left, or some disturbance, some draft, some vibration coming in from outside. There is nothing outside, there is nothing pushing you at all. You cannot hold still because the mathematics of reality itself will not permit it. The law that governs what you are forbids the perfect rest you are trying to reach. So you tremble, forever. A tiny, ceaseless, irreducible trembling that no amount of cold can ever still. That is what it is to be a quantum particle at the bottom of its well. It is to be unable, structurally, permanently, to be at rest. And now widen that picture out, because here is where it stops being about one particle and starts being about everything. The space around you, the empty space in this room, the empty space inside every atom of your body, the empty space stretching out between the stars, is not actually empty in the way the word suggests. It is filled with fields. The most familiar of these is the electromagnetic field, the field responsible for light, for radio, for the forces that hold your body together. And that field is not a single thing. It is, in the mathematics, a vast collection of oscillators. Every possible wavelength of light, every frequency, every direction a wave could travel, every way the field could ripple, is its own separate oscillator, and every single one of them by the same ironclad logic has a zero-point energy. Every one of them is trembling. Every one of them carries that minimum irreducible energy that cannot be removed. So the vacuum, the true vacuum, empty space with everything taken out of it, is not quiet. It is not still. It is a seething, jittering, restless thing, humming at the lowest energy it is permitted to have, which is not zero. Every point of empty space is doing exactly what our single particle was doing, holding the smallest restlessness it is allowed and unable ever to let go of it. This was not a popular idea. For a long time, most physicists did what Einstein wanted to do. They treated zero-point energy as a bookkeeping curiosity, a term you could subtract away, a quirk that did not really mean anything because, after all, only differences in energy are ever measured, so who cares what the baseline is? But there were a few who took it seriously. In 1916, a German chemist named Walter Nernst proposed that all of space, the entire universe, is filled with this zero-point radiation, an ocean of restless energy permeating every point of the cosmos. He was, more or less, ignored. In 1924, a physicist named Robert Mulliken found the first direct experimental fingerprint of zero-point energy. He was studying the light given off by two slightly different versions of the same molecule, boron monoxide, and he found that the patterns in that light only made sense, the numbers only added up, if the zero-point energy was genuinely physically there. And in 1925, when Werner Heisenberg built the first complete version of quantum mechanics, the zero-point energy came out of his equations too, not as an optional extra, but as a mathematical necessity. So by the middle of the 1920s, the situation was this. The best physics in the world was saying clearly and consistently that empty space contains energy, that nothing is not nothing. And almost everyone who heard this preferred not to think about it too hard. But there was one man who did think about it hard. One man who took the idea of vacuum energy and followed it, with brutal honesty, all the way to the end of the road. And what he found waiting for him at the end of that road was so disturbing that he did the only thing he could think to do. He turned around, and he walked away, and he never spoke of it again. Part 3. The number that should have stopped physics. The man who followed the thread to its end was Wolfgang Pauli. And to understand what he found, and why his reaction matters so much, you need to understand who Pauli was. He was not a timid physicist. He was, by reputation, the most ferocious mind of his generation, a man whose criticism was so sharp and so feared that his colleagues had a private joke about it. They spoke of the Pauli effect, the idea that Pauli's mere presence in a room could cause experimental equipment to break. He was famous for a particular kind of dismissal, the line he would use for an idea he considered not just wrong, but unworthy of the word wrong. He would say it was not even wrong. Pauli did not flinch from uncomfortable conclusions. He had, in fact, built his career on one. In 1930, faced with energy that seemed to be vanishing in certain nuclear reactions, Pauli had proposed something almost unthinkable. A new particle, one so ghostly, so weakly interacting, that it might never be detected at all. He apologized for it. He said he had done a terrible thing, postulating a particle that could not be observed. That particle was the neutrino, and 26 years later it was detected, exactly as he had described. Pauli, of all people, knew that physics does not care whether an answer is comfortable. He knew that the universe is under no obligation to be convenient, and so, sometime in the 1920s, Pauli did a calculation. It was not a careful, polished, publication-ready calculation. It was the kind of thing a great physicist does on the back of an envelope, or in his head, to see roughly where a line of reasoning leads. He took the idea seriously that the vacuum is full of zero-point energy, and he asked a simple question. What if that energy gravitates? This is the crucial question, and I need to make sure you feel its weight, so let me slow down here. Einstein's theory of general relativity, which was brand new at the time, says something very specific and very strict about energy and gravity. It says that all energy gravitates. Every form of energy, without exception, bends space, curves the geometry of the universe, pulls on everything around it. There is no kind of energy that gets to opt out. Mass gravitates because mass is a form of energy. Light gravitates heat gravitates, and if the vacuum has energy, if empty space genuinely carries that humming zero-point restlessness, then by the unbreakable rule of general relativity, that energy must gravitate too. It must bend space. It must have consequences for the shape of the entire cosmos. So Pauli did the sum. He took the zero-point energy of the electromagnetic field. He made a reasonable estimate of how much of it there should be, and he asked what its gravity would do to the universe. And the answer he got was a kind of catastrophe. The answer was that the universe, under the weight of its own vacuum energy, would curl up so tightly, would be so violently curved by the gravity of empty space, that the entire cosmos would be smaller than the distance from the Earth to the Moon. Let that land for a moment. Everything, every galaxy, every star, all the billions of light years of space that we now know are out there, the whole observable universe, crushed by the gravity of its own emptiness into a ball you could not even stretch from here to the Moon. The Moon is about 380,000 kilometers away. Light crosses that gap in a little over a second. Pauli's calculation said that if vacuum energy gravitates the way all other energy must, the entire universe would fit inside a region light could cross in about a second. And the universe, very obviously, is not like that. You can look up at night and see, with your own eyes, stars that are hundreds of light years away. The universe is vast. It is almost unimaginably vast. So Pauli's calculation had collided head-on with reality. His mathematics, built on solid quantum physics and solid general relativity, two theories that were both turning out to be spectacularly correct, said the universe should be a tiny crushed point. And the universe was not a tiny crushed point. The universe was enormous and full of stars, and obviously undeniably here. Now here is the part of the story that I find genuinely haunting, and I have thought about it a great deal. Pauli did not get the wrong answer. That is the thing. The math was right. The reasoning was right. If vacuum energy gravitates at anything like its natural value, the universe should not exist in the form we see it. That is a true statement. It is still a true statement today. Pauli had stumbled, decades before anyone else, onto one of the deepest and most disturbing problems in all of physics, a problem that is still unsolved as you listen to this. He saw it. He saw it clearly. He was perhaps the first human being to see it clearly. And he chose to look away. In his great review article on physics, the one that served as a kind of Bible for a generation of physicists, Pauli wrote that it was more sensible to simply exclude the zero-point energy from the calculations altogether. His reasoning was, in essence, this: the energy evidently does not gravitate, because if it did, the universe would be crushed, and the universe is not crushed. Therefore we should leave the energy out. He did not solve the problem. He did not explain why the vacuum energy fails to gravitate when general relativity insists that all energy must. He simply set the troublesome thing aside, declared it a non-issue, and moved on. In a later edition of that same review, he dropped the topic entirely. I do not say this to condemn him. What was he supposed to do? He was a working physicist with 1,000 real problems in front of him, problems he could actually make progress on. And here was a result that said, in effect, the universe should not exist. There was nothing to be done with a result like that. There was no experiment to run, no calculation to refine, no next step. It was a wall. So he turned away from the wall and went back to the work that could be done. Almost anyone would have done the same, and there is a deeper reason Pauli's choice was so natural, a reason rooted in how physics had taught itself to think. For decades, physicists had been trained on a single reliable comfort, that the absolute value of energy does not matter, that only differences matter. You measure how much energy a falling ball gains, not the total energy of the ball relative to some cosmic zero. You can set the zero of energy wherever you like, at the floor, at the ceiling, at sea level, and every prediction comes out the same. This is true, and it is useful, and it is one of the first things a young physicist learns to lean on. So when the vacuum energy turned up as a huge or infinite number, the trained instinct said, immediately and reassuringly, it does not matter. It is just the 0 point. Set it to 0. Move on. Pauli was not being lazy. He was applying a principle that had never once failed him. The trouble, the thing that would not be understood for decades, was that this principle has an exception, and the exception is gravity. Gravity is the one thing in all of physics that does not care about differences, that feels the absolute value, that responds to the total. And so the very habit of mind that made physicists so successful, the habit of ignoring the baseline, was the habit that let the catastrophe hide. Pauli looked away not because he was careless, but because the entire training of his field pointed his eyes elsewhere. But here is what makes the moment a tragedy, rather than a mere oversight. Pauli did the calculation anyway. Most physicists, trusting the comfortable principle, never even bothered to ask what the vacuum energy would do to gravity, because the principle told them not to, Pauli asked. He, almost alone, followed the thread into the territory where the comfortable principle fails. He saw the wall that nobody else even walked up to, and having seen it, having done the very thing his more incurious colleagues never did, he then chose, deliberately, to treat what he had seen as a non-result. He had the rare courage to look, and then he did not have the rarer courage to keep looking. That is the shape of the anchor here. It is not the failure of a small mind. It is the failure of a great one, at the exact edge of a great discovery, choosing the comfort of the known over the vertigo of the wall. But I want you to feel the weight of this moment anyway, because it is the first emotional anchor of our whole story, and it will echo through everything that follows. Here was Wolfgang Pauli, a man who had postulated an undetectable particle and been proven right, a man who knew better than almost anyone alive that physics does not care about comfort, that the universe will be whatever it is regardless of whether we like it. Here was that man, holding in his hands a calculation that pointed at one of the deepest truths physics had ever brushed up against. And he blinked. The answer was too absurd, too large, too impossible. It said the cosmos should be the size of the orbit of the moon, and so the man who never flinched. He set the answer down and he walked away, and the energy of empty space went back to being a thing that polite physicists did not discuss. The vacuum kept its secret a little longer, but not forever. Because while the theorists were busy looking away, the universe was about to do something it has a habit of doing. It was about to leave a fingerprint. It was about to push the energy of empty space directly into the data, into the hard experimental numbers, in a way that no one would be able to ignore. And the man who would catch that fingerprint was not a famous theorist at all. He was a physicist working in the research department of a company that made light bulbs. Part 4. The Light Bulb Factory. His name was Henrik Casimir, and the path that brought him to a light bulb factory in occupied Holland is a story worth telling slowly, because the man matters here as much as the physics. Henrik Brucht Gerhard Casimir was born in 1909 in The Hague, in the Netherlands. He was a prodigy in the full sense of the word. He entered the University of Leiden at 17 years old, and he came under the wing of one of the great physicists of the age, a man named Paul Ehrenfest. Ehrenfest was a teacher of legendary quality and a man of deep, restless intelligence, and he saw immediately what he had in the young Casimir. When he introduced his student to Niels Bohr, the towering figure of quantum physics, Ehrenfest did it with a line that has been quoted ever since. He said, "I bring you this boy. He has already some ability, but he still needs thrashing." Bohr, by all accounts, was delighted. Casimir spent 18 months in Copenhagen with Bohr, and he later described that period as the most intellectually stimulating of his entire life. He watched, from the inside, as quantum mechanics matured from a scattered collection of brilliant guesses into a single unified theory. He absorbed Bohr's particular way of thinking, a way of thinking that was famously indirect, famously slow, a habit of speaking in half-finished sentences that somehow, maddeningly, contained more physics than other men's completed lectures. We will come back to that habit, because it is going to matter enormously. Casimir earned his doctorate at Leiden in 1931, at the age of 22. He was by any measure a young physicist with the brightest possible future. He had a mathematical object named after him already, the Casimir operator, which is still a standard tool in a branch of mathematics called group theory to this day. He went to work as the assistant of Wolfgang Pauli himself, the same Pauli we just met, in Zurich. He was at the absolute centre of the physics world, moving among the people who were rewriting the laws of nature. And then, in 1933, that world delivered a blow that marked Casimir for the rest of his life. His mentor, Paul Ehrenfest, the man who had shaped him, took his own life. Ehrenfest had been suffering for a long time under a crushing depression, a despair worsened by the feeling, the conviction, that physics had moved beyond his ability to contribute to it, that the new quantum mechanics was racing ahead and leaving him behind. He had planned what he did with terrible care. He had written letters, and the act itself was a horror that I will describe only as gently as I can. Before ending his own life, Ehrenfest first ended the life of his youngest son Vasek, a boy with Down syndrome. Casimir, 24 years old, was called back from Zurich, and he found himself suddenly responsible for teaching the classes of a dead man, carrying Ehrenfest's students through their courses for a full year, until the university could find someone to take the position permanently. He wrote about Ehrenfest decades later, and when he did, he wrote with a kind of quiet, controlled grief, the grief of a man who has folded a great sorrow up very small and carried it a long way. The loss shifted something in him. It is impossible to know exactly how a thing like that changes the trajectory of a life. But the trajectory did change. By 1938, Casimir held only a part-time professorship at Leiden, teaching 1 day a week. And then the war came. The German army occupied the Netherlands, and the occupation began to strangle Dutch academic life, choking off the freedom and the resources that science depends on. And so, in 1942, in the middle of the war, in an occupied country, Henrik Casimir made a decision that would have seemed almost unthinkable for a man of his gifts a decade earlier. He took a full-time job in industry. He went to work at the Philips Natuurkundig Laboratorium, the physics laboratory of the Philips Company, in the town of Eindhoven. Philips made light bulbs, it made radios and vacuum tubes and the ordinary electrical machinery that filled European homes. And the research lab Casimir joined was a genuinely serious place, one of the great industrial laboratories of the world. But still, a man who had been thrashed into shape by Bohr himself, who had worked at Pauli's side, who carried the unfinished promise of the quantum revolution, was now going to spend the heart of his career making industrial physics work. He would stay at Philips for 30 years. He would rise to become the director of research, and eventually a member of the board of management, overseeing all of the company's scientific work across the entire world. It was a distinguished career. But it was not the career anyone would have predicted for the boy who entered Leiden at 17. And here is the irony that sits at the very centre of this story, an irony so precise it is almost painful. The discovery that would make Henrik Casimir's name immortal, the result that would force the entire science of physics to confront the nature of empty space, did not come from the great universities. It did not come from Copenhagen or Zurich or Princeton. It came out of that light bulb factory. And it came from the most unglamorous, most mundane, most thoroughly industrial problem you could possibly imagine. The problem was, of all things, the physics of suspensions. A colloidal suspension is what you get when you have tiny particles of one substance spread evenly through another and not settling out. Milk is a colloid, fog is a colloid, mayonnaise is a colloid, and the Philips Company, being a company that manufactured a great many physical products, cared a great deal about how such mixtures behave, about why some of them stay stable and others separate. A physical chemist at the lab named Theo Overbeck had been studying the faint attractive forces that pull colloidal particles toward each other, and he had noticed something odd. At large distances, those forces were weaker than the existing theory predicted. They fell off faster than they should. The particles, when they were far apart, were less drawn to each other than the equations said. Overbeck had an intuition about why. He suspected that the culprit was the finite speed of light. The attraction between two particles comes from the way the cloud of electrons around one particle influences the cloud around the other. But light, and therefore that influence, does not travel instantly. It travels at a fixed and finite speed. And Overbeck guessed that when the particles were far enough apart, the time it took for that influence to cross the gap would degrade the connection, would weaken the force. He could not do the mathematics himself. So he turned to two physicists in the lab, and he asked them to work it out properly. One was Henrik Casimir, the other was a younger colleague named Dirk Polder. Casimir and Polder took the problem and they ground through it. And it was a grind. It was a long, intricate, exhausting piece of quantum physics, dozens of pages of dense calculation, the kind of work that one later physicist would describe as laborious and lengthy. But they got there. They produced a result published in early 1948 that confirmed Overbeck's intuition. At large separations, the attraction between particles really does change its character because of the finite speed of light, weakening into a different mathematical form. It was a solid, respectable piece of work. It was also, as it turned out, the long way around, because then came the mumble. Picture the scene. Casimir, with this laborious result in hand, is visiting Copenhagen. He's back in the orbit of Niels Bohr, the old teacher, the towering mind, and in conversation Casimir mentions the calculation, the dense and difficult thing he and Polder have just finished. And Bohr does what Bohr always did. Bohr appears for a moment to be half asleep. His eyes are heavy. He seems barely to be attending. But behind that drowsy exterior his mind is working at a level that very few human beings have ever reached. He thinks. He pauses, and then he mumbles something. Just a few words. By most accounts it was not even a complete sentence. It was not a paper, not a calculation, not an argument. It was a mumble, an old man's half-voiced thought, drifting across a quiet room. And what he mumbled was something about zero-point energy. That was all. That was the entire contribution. A few mumbled words about zero-point energy, and it detonated in Casimir's mind like a depth charge. Because in that instant Casimir saw it. He saw that the entire laborious calculation, all those dozens of pages, all the intricate machinery of electron clouds and retardation, and the finite speed of light could be thrown away. All of it. He saw that the whole problem could be reframed from the ground up in terms of one single, beautiful idea, the zero-point energy of the vacuum itself. Forget the particles, forget the electron clouds. Think instead, Casimir realized, about what empty space does when you put two metal plates into it. And in that thought, in the space opened up by Bohr's mumble, the most elegant and unsettling result of his life came into focus all at once, like a structure suddenly lit up in the dark. Part 5. 3 pages, and the vacuum that came back as data. So what was it that Casimir saw? Let me walk you through it, because the idea is genuinely beautiful, and you do not need any mathematics to feel its force. Start with the vacuum, the true empty space with its zero-point energy. Remember what we established, that empty space is not still. It is humming with the restless, irreducible jitter of the electromagnetic field, and that field is made of countless oscillators, one for every possible wavelength, every frequency, every way a wave could ripple through space. In open, unbounded, empty space, every wavelength is allowed. The vacuum can hum at any pitch it likes. There is no restriction. Now put 2 flat metal plates into that vacuum, facing each other, close together, and ask what happens to the humming in the gap between them. The answer is that the gap becomes choosy. Metal plates impose a condition on the electromagnetic field. Only certain wavelengths are allowed to exist in the space between them, the wavelengths that fit neatly into the gap, that can complete a whole number of vibrations between one plate and the other. A wavelength that does not fit is simply not permitted there. It is excluded. So between the plates, only some of the vacuum's oscillators are allowed to hum. Outside the plates, in the open space all around, all of them still are. And that means something simple and profound. There are fewer modes of vibration between the plates than outside them. Fewer oscillators means less zero-point energy. The energy density of the vacuum in the narrow gap between the plates is lower than the energy density of the vacuum in the open space outside, and nature, always and everywhere, pushes from regions of higher energy toward regions of lower energy. The vacuum outside the plates, humming with its full range of modes, presses inward harder than the thinned-out vacuum between the plates can press back. The result is a net force. The plates are pushed together, not by anything between them, by the imbalance in the emptiness itself. That was the insight. And when Casimir worked it out, the result was so clean it was almost shocking, especially set beside the dozens of grinding pages of the calculation it replaced. The paper he published later in 1948, with the modest title On the Attraction Between Two Perfectly Conducting Plates, was 3 pages long. 3 pages, and the formula at its heart, the formula for the force, contained almost nothing. It had the plate separation in it, of course, and it had exactly 2 constants of nature. One was Planck's constant, the fundamental constant of quantum mechanics. The other was the speed of light. That was all. The mass of the electron did not appear. The charge of the electron did not appear. No property of any particular particle. No detail of any particular material. entered the formula at all. And that absence is the whole point. It told you, in the starkest possible way, that this force was not a property of the metal or of any substance. It was a property of empty space itself. Let me give you a sense of the numbers, because they are part of what makes this so strange. At a separation of 1 micrometer, which is 1/1,000,000th of a meter, a tiny distance but still vast compared to an atom, the force the vacuum exerts on a square centimetre of plate is about 13/10,000,000ths of a newton. That is a minuscule force. You would never feel it. But the force does not stay minuscule, because it grows ferociously as the plates get closer. It scales as the 4th power of the distance, which means that halving the gap multiplies the force by 16. And so by the time you bring the plates to a separation of 10 nanometers, just a few dozen atoms apart, the pressure the emptiness exerts has climbed all the way to roughly 1 atmosphere. The full weight of the sky generated by nothing in a gap narrower than a virus. When Casimir told Pauli about the result, Pauli's response was immediate and characteristically blunt. He called it absolute nonsense. And there is something almost poignant in that, because this was the same Wolfgang Pauli who, 20 years earlier, had calculated that vacuum energy gravitating at its natural value would crush the universe smaller than the orbit of the moon. Pauli, of all people, knew that the vacuum was not truly empty. He had followed that thread further than anyone, and yet even he, when told that the energy of empty space could reach out and physically push 2 metal plates together, recoiled and called it nonsense. That tells you how deep the resistance ran. The entire physics community had quietly agreed to treat vacuum energy as a bookkeeping fiction, a number with no physical teeth. And here was Casimir saying the number had teeth after all. Proving it, though, took a very long time. Measuring the Casimir force is a nightmare of precision. The force is tiny unless the plates are extraordinarily close, and keeping 2 flat plates perfectly parallel at a separation of a few millionths of a meter is brutally difficult. The tiniest tilt ruins everything. Worse, any stray electric charge on the surfaces, any speck of contamination, any roughness at the scale of atoms can produce forces that swamp the delicate effect you're trying to detect. The first serious attempt came in 1958, when a physicist named Marcus Sparnay, working at Philips, tried to measure it. And his honest conclusion was a masterpiece of careful understatement. He reported that his results did not contradict Casimir's prediction. That is physicist's language. It means the experiment could not actually confirm the prediction. The uncertainty was simply too large to tell. The vacuum had not yet been pinned down. The real confirmation came almost 50 years after the prediction itself. In January of 1997, a physicist named Steve Lamoureux at the University of Washington found an elegant way around the parallelism problem. Instead of trying to hold 2 flat plates perfectly aligned, he used a flat plate and a gently curved one, a sphere, where the geometry no longer demanded perfect alignment. He mounted it on an exquisitely sensitive instrument called a torsion pendulum, and he measured the force, and it was there. It matched Casimir's 1948 prediction to within about 5%. The following year, in 1998, 2 physicists named Umar Mohideen and Anushri Roy, working at the University of California at Riverside, used an atomic force microscope, an instrument capable of feeling forces at almost unimaginably fine scales, and pushed the agreement even tighter to within about 1%. So it was real. After half a century, it was no longer a theorist's claim. It was a laboratory fact. Empty space with nothing between 2 pieces of metal exerts a measurable, repeatable, predictable force on solid objects. Emptiness has a force. Hold on to that phrase because we are going to need it again, much later, when it has grown into something far stranger and far larger than a curiosity in a vacuum chamber. And I want to pause here, just for a moment, on Henrik Casimir himself, because I think he deserves it. He lived a long life. He died in the year 2000 at the age of 90, having watched his prediction confirmed with a precision he very likely never expected to see. He received honours. He received medals and honorary degrees and memberships in the great scientific academies, but he never received a Nobel Prize, and I will say plainly that I think this is one of the quiet injustices in the history of physics. Here was a man who proved with a 3-page paper that emptiness has energy and that the energy has force. He did it not from a famous university, but from a light bulb factory in an occupied country during a world war. He did it on the strength of an old man's mumble, caught and understood in a single illuminated instant. And the prize that goes to the deepest and most surprising discoveries passed him by. The man deserved better than he got. But there is one more thread I have to weave in before we leave this part, because Casimir's plates were not actually the first time the vacuum forced its way into the hard data. There was another result, almost exactly contemporary, that did the same thing from a completely different direction, and the two of them together slammed shut the door on the comfortable old idea that vacuum energy was just a fiction. The year before Casimir's paper, in June of 1947, 24 physicists gathered at a small inn on Shelter Island, off the coast of New York for a 3-day conference. It was a charged moment for physics. The atomic bomb had, just 2 years earlier, made physicists into something close to celebrities. One professional society later wrote that physics had, at that moment, reached the apogee of its public reputation. And the star of that small gathering was a physicist named Willis Lamb. Working with a graduate student named Robert Rutherford, Lamb had performed an experiment of extraordinary delicacy on the hydrogen atom, the simplest atom there is, a single proton with a single electron. He had measured the energy of 2 particular states of that electron, 2 specific configurations it could occupy, and according to one of the most beautiful and successful equations in all of physics, the Dirac equation, those 2 states were supposed to have exactly the same energy. Precisely equal, identical. They were not. Lamb found that one of them sat slightly above the other, by an amount corresponding to a frequency of about 1058 MHz, a small gap. But a gap that, according to the celebrated equation, should not have existed at all. It should have been exactly 0. What was opening that gap? The vacuum. The 0-point fluctuations of the electromagnetic field, the same restless humming of empty space we have been circling all along, were reaching into the hydrogen atom and jostling the electron in its orbit. They were giving it a tiny, ceaseless, random shake, smearing its position out over a minuscule region of space. And because the 2 states Lamb measured had the electron spending its time differently, that smearing affected them by different amounts, nudging their energies apart by exactly the sliver that Lamb had measured. The empty space inside an atom was not empty. It was, measurably, moving the atom's energy levels around. There is a wonderful detail in how the explanation was worked out. After the Shelter Island conference ended, a physicist named Hans Bethe boarded a train home, and on that train, with nothing but the discussions of the conference and the contents of his own formidable memory, Bethe did the calculation. Freeman Dyson once said of Bethe that he never needed to look up a number in a table because he simply knew them all. Bethe carried the constants of the universe in his head the way other people carry the names of streets. And on that train ride, in a couple of pages and a dozen equations, he produced an estimate of the size of Lamb's mysterious energy gap, an estimate that came close enough to the measured value to prove, beyond reasonable doubt, that the vacuum was the cause. So now there were 2 fingerprints, not one. Casimir's plates and Lamb's shifted energy levels. From 2 completely different directions, the vacuum had pushed itself into the experimental data and signed its name. Empty space had energy. That was no longer a philosophical position you could take or leave. It was a measured fact about the world, which makes what happened next so much stranger. Because in the very same year that Casimir published his 3-page paper, the very same year, a small group of the most brilliant physicists alive were finishing a piece of work whose central purpose, whose entire effect, was to take the energy of empty space and make it disappear. Part 6. The year they erased it. To understand what those physicists did, and why, you have to understand the problem they were trying to solve, because they were not villains and they were not fools. They were among the most gifted human beings of the 20th century, and they were facing a genuine crisis. The crisis was infinity. The theory they were building was quantum electrodynamics, usually shortened to QED, and it was meant to be the complete and final description of how light and matter interact, how electrons and photons behave, the physics underneath essentially every phenomenon you experience in daily life. It was a magnificent ambition. And it kept producing nonsense. Every time a physicist tried to use the theory to calculate something real, some property of the electron, some detail of how particles scatter off one another, the equations would, at a certain point, hand back the answer infinity. Not a large number, not a difficult number. Infinity, the mathematical symbol for something without limit, something that has broken free of all bounds, and you cannot compare infinity to an experiment. An experiment gives you a number on a dial. Infinity is not a number on a dial. A theory that predicts infinity for measurable things is, on the face of it, simply wrong. The infinities came from several places, but the one that matters most for our story is the vacuum. Remember what we have established. The electromagnetic field is a vast collection of oscillators, one for every mode, every wavelength, every direction, and every one of them carries a zero-point energy, that irreducible 1/2 hnu. Now add them all up, sum the zero-point energy over every mode of the field, every possible frequency from the lowest all the way up without limit. There is no largest frequency. The modes go on forever, and so the sum goes on forever. The total zero-point energy of the vacuum, calculated honestly with no tricks, comes out to infinity. Even if you cheat a little, even if you decide to stop the sum at some very high frequency, rather than letting it run on forever, the answer is not infinity, but it is still monstrous. If you stop the sum at the so-called Planck scale, the energy scale where physicists expect quantum gravity to become important, the energy density of the vacuum comes out to something like 10 to the 96th kilograms per cubic meter. I will not even try yet to make that number meaningful. I will just say that it is large enough to be a catastrophe, and we will return to exactly how much of a catastrophe later. For now, hold the simple fact. The theory said the energy of empty space was either infinite or impossibly huge. The men who solved the crisis were three, and they solved it independently, on 3 different continents, at almost the same moment. There was Julian Schwinger, a prodigy of almost frightening precocity, a man who published his first physics paper as a teenager and earned his doctorate at 21. There was Richard Feynman, who would become the most famous physicist of the post-war era, a man whose intuition ran so deep and so strange that his colleagues sometimes could not follow it. And there was Shinichiro Tominaga, working in the ruins of post-war Tokyo in conditions of real material deprivation, cut off from the West, who had reached the same destination by his own separate road, in wartime isolation, with no knowledge at all of what the two Americans were doing. A young British mathematician named Freeman Dyson would later prove that all 3 approaches were, underneath their different surfaces, the same theory. Schwinger, Feynman and Tominaga would share the Nobel Prize for it in 1965. And what was the thing they had done? The procedure they had built was called renormalization. And I want to be very careful and very honest about what renormalization actually is, because the textbook version and the real version are not quite the same, and the difference between them is the hinge of this entire story. The textbook version is that renormalization solved the infinity problem. That is true, in a sense, but it is true the way it is true that sweeping dirt under a rug solves the problem of a dirty floor. What renormalization actually does, for the specific case of the vacuum energy, is this. It takes that infinite sum, the monstrous total zero-point energy of all the field's modes, and it subtracts it. It removes it. It declares, by definition, by mathematical fiat, that the energy of the vacuum is zero. The procedure has a technical name, normal ordering, but the plain language description is exactly what it sounds like. The infinite energy is deleted from the equations, and the vacuum is redefined to have no energy at all. The answer was struck out. The answer was erased from the books. Now, I need to be fair because here is the part that makes renormalization not a fraud, but a genuinely deep and defensible idea. In the ordinary physics of particles, in everything that does not involve gravity, this erasure is completely, perfectly legitimate. And the reason comes down to a single principle. Only differences in energy are ever measured. You never measure the absolute energy of anything. You measure how much energy something gains or loses, how much it has relative to something else. The baseline, the 0 point you measure from, is a free choice. It does not affect any prediction. Let me give you the analogy that physicists themselves use because it is a good one. Imagine you are standing on a beach trying to measure the height of the waves. The ocean beneath those waves has a depth. It might be 100 meters deep, it might be 3,000 meters deep, but you do not care. You are measuring waves, not depth. So you set your instrument to call the average surface level 0, and you measure how far the water rises above that line and how far it falls below it. The absolute depth of the ocean, the vast quantity of water underneath, is simply irrelevant to the thing you are measuring. You subtract it away, you set it to 0, and every wave height you report is exactly correct. That is what renormalization does with the vacuum energy. It says, we are measuring energy differences, the energies of particles and their interactions, the way they scatter and decay. The vast infinite ocean of vacuum energy underneath all of that is like the depth of the sea. It is the same everywhere. It does not affect any difference. So set it to 0, subtract it, measure the waves, and forget the depth. And when they did this, when they performed this erasure and built the rest of the theory on top of it, the result was, without exaggeration, the most accurate scientific theory that human beings have ever constructed. Quantum electrodynamics makes a prediction for a particular property of the electron, a quantity called its anomalous magnetic moment, and that prediction agrees with the measured value to better than 1 part in 10 billion. Let me try to make that precision real. It is as if you measured the distance from New York to Los Angeles, the entire width of a continent, and got the answer right to within the thickness of a single human hair. That is the accuracy of the theory built on the erased vacuum energy. It is a triumph. It is arguably the single greatest quantitative triumph in the history of science. So this is the situation at the close of 1948, and I want you to hold both halves of it in your mind at once, because the tension between them is the whole story. On one side, Casimir and Lamb have just proved, from 2 independent directions, that the energy of empty space is real, that the vacuum genuinely hums, that it pushes plates and shifts atomic energy levels, that it leaves fingerprints in the hard data. And on the other side, in the very same year, Schwinger and Feynman and Tominaga have just built the most successful theory in history by taking that same vacuum energy and erasing it, setting it to 0, declaring it gone. Both of these things are true at the same time. The vacuum energy is real and measurable, and the vacuum energy has been deleted from the theory. Physics had, in a single year, both discovered the energy of nothing and written it out of the equations. And for a long time, decades, that did not seem to cost anything at all. The erasure looked free, the deletion looked clean, the waves were measured, the depth was forgotten, and the theory worked beautifully. But the men who built that theory were not entirely at peace with it. They knew, at some level, that they had not really solved the problem. They had performed a maneuver, a successful maneuver, a maneuver that worked, but a maneuver. And in the decades that followed, the 2 greatest of them, the 2 who would stand on the stage in Stockholm and accept the Nobel Prize for this very work, would say so, out loud, in public, in print. They would tell the world that the foundation they had poured was not solid, and almost nobody would listen. Part 7. The Founder's Confession. If you want to know how a working physicist truly feels about a piece of physics, do not read the textbook. The textbook is written to teach, and teaching favours tidiness. Read instead what the physicists say when they are being candid, when they are near the end of their careers and have nothing left to protect. And on the subject of renormalization, the candid statements of the people who invented it are extraordinary. They amount to a confession. Begin with Paul Dirac. Dirac was not one of the 3 who shared the 1965 prize, but he was, in a real sense, the father of the whole enterprise. It was Dirac who, decades earlier, had written down the equation that first married quantum mechanics to Einstein's relativity. The Dirac equation, the very equation whose prediction Willis Lamb had found wanting. It was Dirac who had predicted antimatter before anyone had seen it. He was one of the founding minds of quantum theory, and he was famous, almost to the point of legend, for his silence. Dirac spoke so rarely that his colleagues at Cambridge half-seriously defined a unit of speech, the Dirac, equal to 1 word per hour. When a student once told him, during a lecture, that he did not understand a certain step, Dirac simply stood there, and after a long pause, replied that the student's remark was a statement, not a question, and moved on. But on the subject of renormalization, Dirac was not silent. On this, he spoke, and what he said was blunt and unsparing. Lecturing in the 1970s, he said that he was very dissatisfied with the situation, because the so-called good theory, the triumphant QED, did involve neglecting infinities, and neglecting them in an arbitrary way. And then he said the sentence that I think every person who is interested in physics should know. He said, "This is just not sensible mathematics. Sensible mathematics involves neglecting a quantity when it is small, not neglecting it just because it is infinitely great and you do not want it. Sit with that, because it is a devastating thing for a founder of the field to say. He is saying that the procedure at the heart of the most accurate theory in history is not, by his lights, real mathematics. It is a trick. You are allowed, in honest mathematics, to throw away a quantity when it is tiny, because throwing away something tiny barely changes the answer. You're not allowed to throw away a quantity that is infinite, simply on the grounds that it is inconvenient, that it is in your way, that you do not want it. That is not approximation. That is wishful thinking dressed up as a method." Dirac's final paper, published in 1984, the very year he died, was titled, with no softening at all, "The Inadequacies of Quantum Field Theory." In it he said plainly that the excessively good agreement between the theory and experiment does not prove that the theory is correct. He spent his last year searching for a better foundation, a version of the physics that would be mathematically honest. He never found it. He said he hoped others would continue the search. The search, I should tell you, is still going. Nobody has found it. Now turn to Richard Feynman, who was as different from Dirac in temperament as two human beings can be. Where Dirac was silent, Feynman was a showman, a storyteller, a man who loved an audience. And Feynman too won the Nobel Prize for this work, and Feynman too said in plain public language that he did not trust it. In a book he wrote in 1985, a book meant for ordinary readers, explaining QED to people with no physics training at all, Feynman described renormalization directly. He called it a shell game. He called it a dippy process. He wrote that having to resort to such hocus pocus, his word, hocus pocus, had prevented physicists from proving that the theory of quantum electrodynamics is mathematically self-consistent. And he added, with the bluntness that was his trademark, that he suspected renormalization was not mathematically legitimate. 20 years before that, in his own Nobel lecture, the speech you give when you accept the highest honour your field can bestow, Feynman had described renormalization as simply a way to sweep the difficulties of the theory under the rug. I want you to really absorb the shape of this, because it is genuinely strange. The two greatest figures associated with this triumph, the men whose names are attached to its glory, both stood up, in public, in writing, and said that the method was not legitimate. One called it not sensible mathematics. The other called it hocus pocus, and a shell game and a thing swept under the rug. These are not the words of critics or outsiders or cranks. These are the words of the founders. And the specific thing they were uneasy about, the specific quantity that the shell game made disappear, was the energy of the vacuum. The same energy Casimir had just proved exerts a real, physical force. The same energy Pauli had calculated would, if taken seriously, crush the universe. That was the thing under the rug. Now you might reasonably ask, if the founders themselves said this so plainly, why did the discipline as a whole simply carry on? Why is renormalization taught today, in every graduate physics program in the world, as a settled and respectable technique rather than as the uneasy compromise its inventors called it? And the answer to that question tells you something true and a little uncomfortable about how science actually works, as opposed to the tidy way we usually imagine it working. Science is done by human beings, and human beings, even brilliant ones, even the most rigorous, have a powerful and entirely understandable preference for methods that produce results. Renormalization produced results. It produced the best results anyone had ever seen, agreement with experiment to a precision that bordered on the miraculous. And when a method works that well, a kind of gravity takes hold. The next generation of physicists learns the method not from the doubting founders, but from textbooks, and textbooks are written to instruct, not to agonize. They present the procedure cleanly as a tool, a thing you use, the way you might learn to use a hammer without lying awake wondering whether the hammer is philosophically justified. The doubt does not get passed down. The technique does. And so, generation by generation, the unease of Dirac and Feynman quietly drained out of the discipline, not because anyone had answered their objection, but because the objection simply stopped being mentioned. The procedure worked, and working, in the end, was enough. I do not say this as an accusation, and I want to be careful here. because it would be easy to turn this into a story about cowardly physicists, and that is not the story. And it would not be fair. I say it because it is the honest texture of the thing, and because it matters for everything that follows. The vacuum energy was not erased in a single dramatic act by a single villain. There was no meeting, no decision, no document. It was erased the way most inconvenient truths are quietly erased. Slowly, institutionally, by omission, by 10,000 small and individually reasonable choices to teach the clean version of the story rather than the troubled one. Every one of those choices made sense on its own. Put them together, stretch them across 60 years, and they add up to a discipline that uses a number it has set to 0, while the universe, all around it, insists the number is not 0. The founders confessed, the discipline moved on, and the confession, the genuine and public confession of the men who built the most accurate theory in history, became a kind of footnote, a curiosity, a thing you could find if you went looking but that nobody ever put in front of you. The rug stayed where it was, and the thing underneath it stayed exactly where it was too, patient, undisturbed, waiting for the one part of physics that would not agree to look away. There is a partial rescue, and I want to give it to you fairly, because it is real physics and it matters. It came in the early 1970s from a physicist named Kenneth Wilson, and it is one of the genuinely deep ideas of the century. Wilson developed something called the renormalization group, and what it showed was that physical theories naturally change their character, depending on the scale at which you look at them. A theory that describes the world beautifully at the scale of atoms is not obligated to keep working at scales a trillion times smaller. Wilson showed that the infinities of QED arise in large part from a naive and unjustified assumption. The assumption that a theory which works at the energies we can reach must keep working all the way up to infinitely high energy. Stop making that assumption, Wilson said. Treat QED as what physicists now call an effective theory, a theory that is valid within a certain window of scales and is simply not expected to apply outside that window. Do that, and the infinities stop looking like a fatal disease. They start looking like an artifact, a symptom of asking the theory a question it was never built to answer. This is a beautiful and a true idea, and it earned Wilson his own Nobel Prize, and it made renormalization respectable in a way it had not been before. For the physics of particles, for QED and the theories that came after it, the Wilson picture is deeply satisfying. It tells you that you do not need to panic about the infinities, because the infinities live at scales where your theory was never meant to go. But, and this is the hinge, the Wilson rescue does not reach the vacuum energy problem. It cannot. Because Wilson's idea works by saying, in effect, do not worry about the high energy stuff, it is outside your theory's range. And that is a fine thing to say when you are calculating how electrons scatter, because the scattering of electrons does not care about the energy you have declared off limits. But the vacuum energy is not like the scattering of electrons. The vacuum energy has gravity, and gravity, as we are about to see in detail, does not honour your declared range of validity. Gravity does not accept the Wilson bargain. Gravity reaches into every scale, the ones inside your theory and the ones outside it, and it adds up everything it finds. You can tell your particle physics to ignore the vacuum energy. You cannot tell gravity to ignore it. And that single fact is the reason the erased answer could not stay erased. It is the reason the deletion, which looked free for 50 years, was about to come due. Part 8. Where the ocean analogy breaks. We have been carrying an analogy for a while now, the ocean and the waves, and it has served us well. It explained, cleanly and honestly, why renormalization is legitimate in ordinary physics. You measure the waves, you ignore the depth. The depth does not matter, because it is the same everywhere and only differences are measured. For all the physics of particles, that picture holds. But every analogy has a breaking point, a place where it stops describing reality and starts misleading you. And the ocean analogy has a breaking point, and the breaking point is gravity. So I want to take this part slowly, because the moment the analogy breaks is the exact moment our story turns from a triumph into a catastrophe. Why does the depth of the ocean not matter for waves? Because waves do not feel the depth. Not really, not in the open sea. A wave 100 meters tall behaves essentially the same, whether the water beneath it is 1 kilometer deep or 10. The depth is, for the purpose of the waves, invisible. It is a quantity you genuinely can set to zero with no consequence, because nothing you care about responds to it. But now suppose you had something that did respond to the depth. Suppose you had an instrument that felt not the height of the waves, but the total weight of all the water, every drop of it, from the surface all the way to the seabed. For that instrument, the depth is everything. The depth is the whole measurement. You could not set it to zero. You could not subtract it away and pretend it was not there, because the instrument is built precisely to feel the thing you would be pretending away. Gravity is that instrument, and here is the principle, the strict and unbending principle, that makes it so. In Einstein's general relativity, all energy gravitates. I said this before, back when we met Pauli, but now it becomes the load-bearing wall of the whole structure, so let me state it as sharply as I can. Energy bends space. Every form of energy, with no exceptions and no opt-outs and no special cases, contributes to the curvature of space-time, contributes to gravity, pulls on the geometry of the universe. There is no kind of energy that gravity does not see. There is no energy that gets to be invisible to gravity the way the ocean's depth is invisible to the waves. And so the vacuum energy, the depth of our ocean, the thing that renormalization sets to zero, is not actually invisible. It only looks invisible if all you're doing is particle physics, because particle physics, like the waves, responds only to differences. But gravity is not particle physics. Gravity responds to the total. Gravity feels the depth. And when you ask what the vacuum energy does to gravity, to the actual large-scale shape of the universe, you are no longer allowed to set it to zero. The bookkeeping trick that was perfectly legitimate for the waves is illegitimate, is simply false, the moment gravity enters the room. I want to make sure this is not abstract, so let me give it to you one more way, with a different image, because it is the pivot of the entire night. Imagine two accountants given the same ledger. The first accountant is asked only one kind of question. How much did this account change between January and June? For that accountant, the starting balance is irrelevant. Whether the account began the year holding $100 or $100 billion, the change over 6 months is the same, and the first accountant can, with perfect honesty, set the opening balance to zero and simply track the movement. The second accountant is asked a different kind of question. What is the total weight of all the gold in the vault right now, in absolute terms? For the second accountant, the opening balance is everything. There is no setting it to zero. The number you ignored is the number being asked for. Particle physics is the first accountant. It asks only about changes, about differences, about the energy released here and absorbed there. And for that work, the vacuum energy genuinely can be set to zero with no harm done. But gravity is the second accountant. Gravity asks for the total. Gravity wants the absolute weight of everything, including the weight of the vacuum, including the very baseline that particle physics was free to discard. And so the same ledger entry, the vacuum energy, is correctly ignored by the first accountant, and cannot possibly be ignored by the second. It is not that one of them is wrong. It is that they are answering different questions, and the entry that is invisible to one is the whole answer to the other. This is the heart of it. This is the thing I most want you to carry away from tonight. When Schwinger and Feynman and Tominaga subtracted the vacuum energy and set it to zero, they were doing something completely correct and completely justified for the physics they were doing, the physics of particles and light. And they were, at the very same moment, doing something completely illegitimate for cosmology, for the physics of the universe as a whole. The same act, the deletion of the vacuum energy, is valid in one domain and invalid in the other. It is valid for the waves and invalid for the weight of the sea. Renormalization did not solve the vacuum energy problem. It walked past it. It walked past it so smoothly, and the resulting theory worked so spectacularly, that for 50 years almost nobody noticed that the problem was still standing there, untouched, in the one place the trick did not reach, the domain of gravity. For a long time, even this might have been left alone, filed under interesting but academic. Because to actually make the problem bite, somebody had to connect the vacuum energy of quantum theory to a specific, measurable feature of the real cosmos. Somebody had to show that the depth of the ocean was not just a number in an equation, but a thing the universe was visibly doing. And that connection was made in 1967 by one of the most remarkable scientists of the 20th century, a man most people outside physics have never heard of. His name was Yakov Zeldovich, and his life is worth a moment of your attention, because it is genuinely extraordinary. Zeldovich was born in 1914 in Minsk. He never, in any conventional sense, went to university. He finished high school at 15. He took a job at 17 as a laboratory assistant, washing glassware and calibrating instruments, and he educated himself in physics by reading the papers the senior researchers left lying on their desks. He attended some university lectures here and there, but he never formally enrolled as a registered student and never collected an undergraduate degree, because he was simply too busy doing real physics to bother with the paperwork. He earned the Soviet equivalent of a doctorate at 22 on the strength of research he had already published, the formal degree made almost irrelevant by the work itself. He became a central figure in the Soviet nuclear weapons program, the first head of the theoretical division at the secret nuclear city where the Soviet hydrogen bomb was designed. He was named a hero of socialist labour 3 separate times, an honour so rare that across the entire history of the Soviet Union, only a handful of people received it even once. The Soviet state considered him one of the most valuable human beings in the country. And then, in the 1960s, apparently having decided that designing thermonuclear weapons was no longer a sufficient intellectual challenge, Zeldovich simply turned, with the same explosive creativity, to astrophysics and cosmology. He helped explain what powers quasars. He predicted an effect, now named partly after him, that distorts the light of the early universe as it passes through clusters of galaxies, an effect that has become one of the most important tools in all of observational cosmology. During a visit by Stephen Hawking to Moscow, it was Zeldovich and a student of his who first suggested to Hawking the idea that rotating black holes might spontaneously emit particles, an idea that directly seeded what became known as Hawking radiation. The man with no undergraduate degree became one of the broadest and most powerful scientific minds of his century. And in 1967, Zeldovich published a short paper that did the crucial thing. It connected the vacuum energy of quantum field theory to the structure of the cosmos. His argument was elegant and, once you see it, hard to escape. The vacuum, Zeldovich pointed out, has to look the same to every observer, no matter how fast they are moving. This is not an optional assumption. It follows from the deepest symmetries of Einstein's relativity, symmetries that are built into the very structure of every quantum field theory we have. Empty space cannot have a preferred direction or a preferred speed. If it did, it would not be empty space. It would be a substance with a state of motion. And Zeldovich showed that this single requirement, that the vacuum look the same to everyone, forces the vacuum energy to behave in a very particular way. It forces it to act exactly, mathematically exactly, like a quantity that Einstein had introduced into his equations half a century earlier and then famously abandoned. It forces the vacuum energy to act like the cosmological constant. Before Zeldovich, the vacuum energy was an embarrassing infinity in particle physics, a thing you swept under the rug and forgot. After Zeldovich, it was something else entirely. It was a contribution to the cosmological constant, and the cosmological constant is a thing you can measure. It is a thing the universe wears on its sleeve, written into the expansion of space itself. Zeldovich had taken the depth of the ocean and shown that it was not hidden after all. He had shown you could weigh it. He had shown you could compare the number that quantum theory predicts for the energy of empty space against the number the actual sky reveals. And once you can do that comparison, once you can put the prediction and the observation side by side, you are no longer looking at an academic puzzle. You are looking at the largest, most catastrophic mismatch between theory and reality in the entire history of science. Part 9. The worst prediction ever made. So let us do the comparison. Let us put the two numbers side by side, the number physics predicts for the energy of empty space, and the number the universe actually contains, and let us look, honestly, at the size of the gap between them. I will warn you in advance that the gap is so large that ordinary language begins to fail, that the numbers stop feeling like numbers and start feeling like a kind of vertigo. But I will do my best to make it real, because the size of this failure is the thing the whole story has been building toward. Here is the prediction. Quantum field theory asked for the energy density of the vacuum, with the sum cut off sensibly at the Planck scale, returns a value of roughly 10 to the 96th kilograms per cubic meter. Here is the observation. The actual energy density of empty space, measured by spacecraft studying the faint glow of the early universe, and calibrated against the distances of exploding stars is about 6 times 10 to the minus 27th kilograms per cubic meter, and the ratio between those two numbers, between what the theory predicts and what the universe actually has, is about 10 to the 123rd, a one followed by 123 zeros. That number is too large to feel. So let me try to walk you up to it, one step at a time. There are, in the entire observable universe, roughly 10 to the 80th atoms. That is every atom, in every grain of dust, in every planet, in every star, in every one of the 2 trillion galaxies that our telescopes can see. All the matter in all of existence, counted atom by atom, comes to about 10 to the 80th. Now, the mismatch between the predicted vacuum energy and the observed vacuum energy is 10 to the 120th or so, which means the error in the prediction is not merely larger than the number of atoms in the universe. It is larger than the number of atoms in the universe by a factor of 10 to the 40th. The wrongness of the prediction outnumbers every atom in existence, and then outnumbers it again, by an amount as large as 10,000 trillion. Let me try it a different way, a more human way. Imagine you're asked to predict the weight of a newborn baby. You do your calculation, and the answer your calculation gives you is not 7 pounds, not 8 pounds. It is not the weight of a car, or the weight of a mountain, or the weight of the Earth. It is not even the weight of the Sun, or the weight of the entire Milky Way galaxy with its 400 billion stars. The answer your calculation hands you, for the weight of one newborn baby, is a number larger than the mass of the entire observable universe, and not just larger by a factor of roughly a trillion. That degree of wrongness, that baby heavier than every galaxy combined many times over, would still be a smaller error than the vacuum energy prediction. That is the worst prediction in the history of science. That is what physics gets from its most trusted theory when it asks the simplest possible question about empty space. And here is the second twist, the one that sharpens the strangeness into something almost unbearable. The problem is not only that the prediction is too big, the problem is the very specific way it is wrong. If the vacuum energy were truly enormous, the universe would be destroyed. We met this already with Pauli. At its natural value, the gravity of the vacuum energy would curl space up so violently that the cosmos would be crushed smaller than the orbit of the moon. No galaxies, no stars, no structures of any kind. Just space folding in on itself, too curved for anything to exist. But the universe is not crushed. You are here. The galaxies are here, vast and spread out and serene, which means that something has reduced the vacuum energy from its natural catastrophic value down to the almost imperceptible whisper we actually observe. Something has cancelled it, and the cancellation is not perfect, because the observed value is not exactly 0, it is just extraordinarily tiny. So whatever is doing the cancelling has not erased the vacuum energy completely. It has erased it almost completely. It has cancelled it to a precision of about 1 part in 10 to the 120th. It has taken a catastrophe and trimmed it down, with breathtaking exactness, to a value just barely above nothing. Think about what that level of precision means. If the vacuum energy were even a few hundred times larger than the value we observe, not 10 to the 100th times larger, just a few hundred times, then the early universe would have flown apart too fast for gravity to ever pull matter together. No galaxies could have formed, no stars, no planets, no chemistry, no biology, no listeners, no one. The cosmos would be a thin, expanding, sterile haze. Every galaxy you have ever seen a photograph of, every star, every planet, every molecule of the DNA inside your own cells, exists because the vacuum energy sits tuned to within roughly 1 part in 10 to the 120th of the value that the deepest theory says it should naturally have. That is the most precise fine-tuning of any quantity in all of known physics, and no one, anywhere, can explain why. I want to slow down here, because this is the second great emotional anchor of our story, and it deserves to land fully. You exist. You are here, listening to this, somewhere in the dark, perhaps drifting towards sleep. And the fact that there is a you to be here at all rests on a number. It rests on the vacuum energy being not its natural world-ending value, and also not exactly 0, which would at least be clean, which would at least feel like a law. It rests on the vacuum energy being something stranger than either of those, a value almost cancelled, almost gone, but not quite. The almost. You're alive because of the almost. Had the cancellation been perfect, the story would be tidy, and a tidy story would feel like an explanation. Had there been no cancellation, you would not exist to mind. Instead, the universe handed you the in-between, the not quite. A coincidence so precise that to call it a coincidence feels almost like a failure of nerve, and to call it anything else feels like a leap past the edge of what we can honestly claim. You are balanced on that knife edge right now. You always have been. Everything you have ever loved has been. Now, I have to be honest with you about one thing, because intellectual honesty matters more than a clean story, and you are an audience that can handle the complication. That headline figure, 10 to the 120th, the one that gets called the worst prediction in physics, depends on a particular choice in the calculation, a hard cut-off placed at the Planck scale, and there are serious physicists who argue that this choice is not quite fair. The physicist Sabine Hossenfelder, among others, has argued that if you do the calculation more carefully, using a more principled mathematical method and the actual measured masses of the known particles, the mismatch is not 10 to the 120th, it is more like 10 to the 55th or 10 to the 60th. The contribution from one well-understood part of physics alone, the part confirmed by the discovery of the Higgs particle at the world's largest collider, already gives a mismatch of about 55 orders of magnitude, and Hossenfelder has argued with real force that calling this the worst prediction in physics is somewhat misleading, because the cosmological constant is, in the structure of general relativity, a free parameter, a number the theory allows you to simply measure rather than derive, and the assumption that quantum vacuum energy must fix its value is itself an unproven assumption about a quantum theory of gravity that nobody has yet written down. I think she has a real point, and I wanted you to hear it. But I also think it matters less than it first appears, and here is why. Even the conservative number, even the modest, careful, defensible figure of 55 orders of magnitude, describes a failure of understanding so vast that nothing else in the history of any science comes anywhere close to it. 55 orders of magnitude means the prediction is wrong by a factor of 1 followed by 55 zeros. And there is something almost more unsettling in the modest version than in the dramatic one, because notice what it means that physicists cannot even agree among themselves whether the error is 55 orders of magnitude or 120. They cannot agree on the size of their own mistake. The disagreement itself, the fact that the discipline cannot pin down whether it is catastrophically wrong or merely staggeringly wrong, is a measure of how poorly the thing is understood. Whether the gap is 60 orders of magnitude or 120, the conclusion does not change. Something is profoundly, fundamentally, structurally wrong with our understanding of empty space. The answer was erased from the books, and the universe has been quietly, patiently insisting on a correction ever since. Part 10. Einstein's discarded constant. I have mentioned the cosmological constant several times now, always in passing, always as a thing we would come back to. We have arrived. And the history of the cosmological constant is one of the great ironic arcs in all of science, a story of a man discarding the very idea that would turn out to describe the universe he lived in. It is worth telling properly, slowly, because it folds our entire story back on itself in a way that I find genuinely beautiful. Go back to 1917. The First World War is grinding on. Albert Einstein has, 2 years earlier, completed general relativity, his theory of gravity, the deepest reimagining of space and time that anyone had ever produced, and he is now doing something audacious. He is applying the theory not to a planet or a star, but to the entire universe at once. He wants to write down the equations that govern the cosmos as a whole, and he runs into a problem. Einstein believed, as essentially every scientist of his era believed, that the universe was static, eternal, unchanging on the largest scale, not expanding, not contracting, just there, the same yesterday and tomorrow and a billion years hence. But his own equations would not allow it. General relativity, applied to a universe filled with matter, said that universe must move. The gravity of all that matter would pull it together. A static universe would begin, inexorably, to collapse. The mathematics simply would not hold still. So Einstein added a term. He introduced into his field equations a new quantity, represented by the Greek letter lambda, and he called it the cosmological constant. What lambda did was provide a kind of repulsion, a pressure built into space itself that pushed outward, that counteracted the inward pull of gravity. Tuned just right, lambda could balance the collapse. It could hold the universe still. It could give Einstein the static, eternal cosmos he believed in. One of his contemporaries, the physicist Willem de Sitter, put the role of lambda vividly. He asked, "What is it, then, that causes the expansion? Who blows up the rubber ball?" And the answer, he said, is that lambda does it. Then came 1929, and Edwin Hubble, and the most consequential observation in the history of astronomy. Hubble, studying distant galaxies, found that they were not sitting still at all. They were receding. They were flying away from us, and the farther away a galaxy was, the faster it was going. The universe was not static. It was expanding. It had been smaller in the past and was growing larger with every passing moment. And in that instant, the entire reason for the cosmological constant evaporated. Einstein had introduced lambda for one purpose only, to hold a static universe still against gravity's pull. But if the universe is expanding, you do not need a repulsion to prevent its collapse. The expansion already prevents the collapse. The motion itself does the job. Lambda had become a solution to a problem that did not exist. So Einstein dropped it. He removed the cosmological constant from his equations, in a paper in 1931 and again the next year. And in a letter written years later, in 1947, to the Belgian physicist and priest Georges Lemaitre, Einstein confessed that since he had first introduced the term, he had always had, in his words, a bad conscience about it. He found it ugly. He found it inelegant, an unjustified blemish on the clean structure of his theory. I want to dwell for a moment on what the cosmological constant actually is, physically, because it is easy to let the phrase wash past as just a piece of jargon, and it is far stranger than that. Ordinary gravity, the gravity of the sun and the earth, and every star, is attractive. It pulls, it draws things together. That is the only kind of gravity our intuition knows. But the cosmological constant is a source of gravity that pushes. It is, in the language of Einstein's theory, a form of energy with negative pressure, and negative pressure in general relativity gravitates outward rather than inward. This is the deeply counterintuitive thing. We are used to pressure pushing outward in the ordinary sense, the way the air in a balloon pushes on its walls. But in Einstein's theory, the gravitational effect of pressure runs the other way, and so a thing with negative pressure, a thing that is, in a sense, under tension rather than compression, produces a repulsive gravity, an anti-gravity woven into the fabric of space. The cosmological constant is exactly that. It is a tension in the vacuum, and that tension, through the strange machinery of general relativity, pushes the universe apart. When Einstein wanted his static universe, he needed precisely this, a built-in outward push to balance the inward pull of all the matter. Lambda gave it to him, and here is the connection that makes the history so resonant. Remember Zeldovich and his 1967 result. Zeldovich showed that the energy of the quantum vacuum, the zero-point energy, must, because empty space looks the same to every observer, behave exactly like the cosmological constant. It must have that same strange equation, that same negative pressure, that same outward push. So the cosmological constant and the vacuum energy are not two separate things that happen to resemble each other. They are, as far as anyone can tell, the same thing seen from two directions. Einstein arrived at it from the top down, from the geometry of the whole universe, asking what term he needed to hold the cosmos still. The quantum physicists arrived at it from the bottom up, from the restless jitter of the fields, asking what energy empty space must contain, and they met in the middle, at the same number, the same lambda, the same tension in the nothing. Einstein's discarded term and the QED pioneers' erased infinity were, all along, a single object. There is a famous story, which you have probably heard, that Einstein called the cosmological constant the biggest blunder of his life. I should tell you that the provenance of that exact phrase is genuinely contested. It comes to us second hand through a physicist named George Gamow, who was a brilliant man but also a notorious embellisher of stories, and historians have argued for decades about whether Einstein ever really said those precise words. Some careful scholarship suggests the phrase was Gamow's polishing. Other careful scholarship, including independent recollections from the highly respected physicist John Wheeler, suggests Einstein really did express the sentiment, even if the exact English wording was tidied up in the retelling. But here is the thing. Whether Einstein said the precise words "biggest blunder" hardly matters, because the deep irony of the story does not depend on the phrase. The deep irony is this. The cosmological constant, the term Einstein introduced and then discarded as ugly and unnecessary, the term he had a bad conscience about, the term he removed from his equations and hoped never to think about again, did not stay buried. It is today the leading description of the dark energy that we now know dominates the entire universe. The thing Einstein threw away came back, and it came back as the most important single component of the cosmos. So if there was a blunder, the blunder was not introducing the cosmological constant. Introducing it, it turns out, was closer to a stroke of accidental genius. The blunder, if there was one, was discarding it. The blunder was looking at a strange, ugly, inconvenient term in the equations, a term that did not fit the universe he expected, and deciding to erase it. And does that not sound familiar? Does that not echo, almost exactly, the thing Schwinger and Feynman and Tominaga would do with the vacuum energy 2 decades later? A strange term appears in the mathematics. It is inconvenient. It does not fit the universe the physicists expect. And so it is erased, struck out, set aside. Twice in the history of physics, the same shape of mistake. And both times the erased thing was, in the end, the same thing. The energy of empty space, the cosmological constant, the quiet pressure built into the vacuum itself. Einstein erased it in 1931, the QD pioneers erased it in 1948, and in 1998, the universe was going to force all of it back into the light, through a discovery that nobody wanted, that nobody predicted, and that 2 rival teams of astronomers fought their way to almost against their own will. Part 11. The universe speeds up. For most of the 20th century, cosmologists believed they knew the broad shape of the universe's future, even if they did not know which of a few options it would choose. The universe was expanding. Everyone agreed on that since Hubble. An expansion meant the universe was full of galaxies all flying apart. But all those galaxies also had gravity, and gravity pulls. So the obvious expectation, the thing every textbook taught, was that the expansion must be slowing down. The galaxies were rushing outward, yes, but their mutual gravity was acting as a brake, dragging on that outward rush, decelerating it. The only real question was how strong the brake was. Maybe gravity was strong enough to eventually halt the expansion altogether and pull everything back, ending the universe in a fiery collapse, a big crunch. Maybe gravity was too weak for that, and the universe would expand forever, but always slowing, always coasting against the drag. Maybe it was balanced exactly on the knife edge between those fates. 3 possibilities. But notice the one thing all 3 of them shared. The assumption underneath every option on the menu. Every single one of them involved deceleration. Every one of them assumed the brake was on. The expansion was slowing. The only question was by how much. Nobody, and I mean genuinely nobody, in the mainstream of cosmology expected anything else. In the 1990s, 2 teams of astronomers set out, independently and as fierce rivals, to measure the deceleration, to pin down, finally, how hard the brake was pressing. Their tool was a particular kind of exploding star, a type of supernova that is extraordinarily useful because it always detonates with very nearly the same intrinsic brightness. That consistency makes these supernovae into something precious. Standard candles. If you know how bright a thing truly is, and you measure how bright it appears, you can work out how far away it is, because distance dims light in a precise and known way. So a supernova of this type, anywhere in the universe, is a distance marker. Find enough of them at enough different distances, and you can map the expansion of the universe across cosmic time. One team was the Supernova Cosmology Project, led by a physicist named Saul Perlmutter, based at a national laboratory in California. The other was the High Z Supernova Search Team, co-founded by a young astronomer named Brian Schmidt, with a researcher named Adam Rees leading much of its data analysis. The 2 teams did not like each other very much. The rivalry was sharp and sometimes bitter. Each group quietly suspected the other of sloppiness, of mishandled calibration, of systematic errors that would invalidate their results. They were racing, and they were both, without knowing it, racing toward the same impossible finish line. Here is the logic they were applying, and you need it to feel the shock of what came next. In a universe where the expansion is decelerating, where the brake is on, distant supernovae should look slightly brighter than you would naively expect. The reasoning is subtle but sound. If the expansion was faster in the distant past and has been slowing ever since, then the most distant supernova, whose light has travelled the longest to reach us, are not quite as far away as a simple, constant speed extrapolation would suggest. And nearer than expected means brighter than expected. So the teams went looking for distant supernovae that were a little too bright. That was the signature of deceleration. That was what they expected to find. Now I want to bring you into a specific room, on a specific kind of night, because this is the third scene moment of our story, and it is the one that turns everything. Adam Rees has the data from the High Z team's most distant supernova. He sits down to analyse it. He runs the light from those far-off stellar explosions through his analysis code, the software built to extract, from all those careful measurements, the shape of the cosmic expansion, and the code, written on the universal and unquestioned assumption of a decelerating universe, returns an answer. It returns a negative mass for the universe, a negative mass. That is not a surprising result. It is not an interesting result. It is an impossible result, a physically meaningless one, like being told a length is less than nothing, or that a box contains fewer than 0 apples. Mass does not come in negative amounts. So Rees does what any careful scientist does when the code returns nonsense. He assumes he has made a mistake. He goes hunting for the bug. He combs through his software line by line looking for the error. He finds none. He turns to the data itself, checking for contamination, for some corrupted measurement, some star that is not what it seems. The data is clean. He checks the calibration, the painstaking chain of reasoning that converts raw telescope readings into true brightnesses and true distances. The calibration holds. Everything he can check, he checks, and everything is clean. The negative mass will not go away. Picture him there, alone with that result, late, the impossible number sitting on the screen in front of him, refusing to dissolve. Because slowly, as he eliminates every ordinary explanation, a different understanding has to start forming. The code is not broken. The data is not corrupt. The negative mass is not an error. It is the code's way of screaming that its single foundational assumption is wrong. The code assumed deceleration. It assumed the brake was on, and it was handed data that simply could not be fitted to a decelerating universe no matter what, and so it had thrown back the only thing it could, an absurdity, a flag, a negative mass, meaning, your premise is false, start over. The distant supernovae were not too bright. They were too faint. They were 10 to 15% farther away than a decelerating universe could possibly place them. And there is only one thing that means. The expansion of the universe is not slowing down. It is speeding up. The brake is not on. There is no brake. There is instead a foot on the accelerator. Something, some form of energy spread through all of space, with a strange outward push, a negative pressure, is driving the galaxies apart faster and faster with every passing eon. Both teams found it. That is the part that makes it bulletproof. Two rival groups, each one half expecting to catch the other in a mistake, each one analysing its own separate set of supernovae with its own separate methods, were forced by their own data to the same staggering unwanted conclusion. The High Z team published first in 1998. The Supernova Cosmology project confirmed it the following year. The rivalry, in the end, became the discovery's greatest strength. You could not blame this on one team's error, because two teams who would have loved nothing more than to find each other's errors had instead found the same impossible thing. They needed a name for the mysterious energy doing the accelerating. A cosmologist named Michael Turner supplied it. He considered calling it funny energy, which I rather wish had stuck before settling on the term that did stick, dark energy. And his reasoning for the name was revealing. He deliberately did not want to call it the cosmological constant, even though it behaved like one, because he said calling it that would make people stop looking for a deeper explanation. The name dark energy was chosen to keep the mystery open, to keep it honest, to remind everyone that we had measured a thing without understanding it. Perlmutter, Schmidt and Rees would share the Nobel Prize for the discovery in 2011. And now, look at what had happened. Look at the whole shape of it. The vacuum energy, The energy of empty space had been discovered to be real by Casimir in 1948. It had been erased from the equations of physics that same year by renormalization. It had been connected to the cosmological constant by Zeldovich in 1967, which made it, in principle, measurable. And now, in 1998, it had been measured. Not in a laboratory, not between two metal plates, but across the entire observable universe, by reading the light of exploding stars. The verdict of that measurement was final and unambiguous. The vacuum energy is not zero. The thing that renormalization set to zero, the thing physics erased from the books, is not zero. It is real. It is tiny, almost unimaginably tiny, a faint whisper of a value, but it is positive, and it is winning. It is the dominant component of the universe, and it is pushing every distant galaxy away from every other, harder and harder, without end. Emptiness has a force. We earned that phrase back in the laboratory with Casimir's plates, where it meant a quaint and delicate curiosity, two small pieces of metal drawn gently together in a vacuum chamber. Hold the phrase now, and feel how it has changed. Emptiness has a force, the same emptiness, the same energy of the same vacuum. But it is no longer a curiosity, and it is no longer gentle, and it is no longer small. It is the engine of the cosmos. It is the force that moves galaxies. The erased answer did not stay erased. It came back wearing the whole sky. Part 12. The slow closing of the sky. So we arrive at the last part, and the question that has been waiting for us since the very first sentence. If empty space has energy, if the vacuum carries a real and positive force, if that force was discovered and then erased and then came back as the thing accelerating the universe, then what does it mean? Where does it leave us? And where, in the deep future, does it leave everything? Let me start with the strangest property of dark energy, the property that makes the future so unlike the past. Ordinary things thin out as the universe expands. Take a box of gas and let the box grow larger. The gas inside becomes more dilute, because the same amount of stuff is now spread through more room. Matter behaves this way. Radiation behaves this way. As space expands, the density of everything familiar drops. But dark energy does not do this. Dark energy, if it truly is the energy of the vacuum, is a property of space itself. And so, every new cubic meter of space that the expansion creates comes into being already carrying its own full measure of dark energy. The vacuum does not get diluted by expansion, because the vacuum is what is expanding. More space simply means more vacuum, and more vacuum means more dark energy, and more dark energy means a stronger outward push, which means the expansion accelerates, which creates space faster, which creates dark energy faster still. It is a feedback loop with no break and no off switch. The more the universe expands, the harder it is pushed to expand. And so, if dark energy holds steady, if it is truly a constant property of the vacuum, then the expansion of the universe does not merely continue. It runs away, it accelerates, and the acceleration itself accelerates forever. Now let me tell you what that means for the sky. Right now, on a clear dark night far from city lights, you can look up and see, with your unaided eye, a few thousand stars in the soft band of our own galaxy. With a telescope you can see more. Other galaxies, thousands of them, millions, the faint smudges of island universes scattered across billions of light years. The universe, to us, is full. It is crowded with light. We are living, though we rarely think of it this way, in a privileged and fortunate age, an age when the cosmos is still legible, still rich, still generous with what it shows. But the accelerating expansion is, very slowly, taking that away. As the expansion runs away with itself, the distant galaxies are not just moving away from us. The space between us and them is stretching faster and faster, and there is a threshold, a horizon, beyond which a galaxy is receding so quickly, carried on so much swelling space, that the light it emits can never again cross the widening gap to reach us. One by one, over enormous stretches of time, the galaxies are crossing that horizon. One by one, their light is being stretched and dimmed and redshifted toward invisibility. One by one, they are slipping out of the observable universe, not destroyed, but placed permanently beyond reach, beyond sight, beyond any possible contact, forever. And here is the final emotional anchor of our story, the one I want to leave you holding as you drift off tonight. Imagine a civilization very far in the future, not millions of years from now, but billions upon billions, far enough that the accelerating expansion has done its slow and patient work. Imagine the astronomers of that civilization. They are intelligent, they are curious, they build telescopes, the finest their science can produce, and they turn those telescopes on the night sky, and they ask the same question we ask, what is out there? And what they see is their own galaxy, and nothing else. Their own island of stars, the merged remnant of what was once the Milky Way and its neighbours, sitting alone in a perfect, absolute, unbroken blackness. Every other galaxy will have crossed the horizon. Every other galaxy will be gone, its light forever unable to arrive. Those future astronomers will look out, and they will see no evidence, none at all, that anything exists beyond their own shore. They will have no way of knowing about the 2 trillion other galaxies, no way of discovering the expansion, because there will be nothing left in the sky whose motion could reveal it. No way of finding the faint glow of the universe's beginning, because the expansion will have stretched that glow into undetectable nothing. They will reasonably, rationally, scientifically conclude that their galaxy is the whole of the universe, an eternal island in an eternal void, and every word of that conclusion will be wrong. The truth will simply have been carried beyond their reach by the quiet, ceaseless force of the energy of empty space. That is what the erase number does. That is what was hiding inside the deletion. When Schwinger and Feynman and Tominaga set the vacuum energy to 0, when Pauli looked away from it, when Einstein discarded his constant, they were not erasing an abstraction. They were setting aside the thing that determines what the last conscious beings in the universe will ever be able to see. The vacuum energy is writing the final chapter of the cosmic story, and the chapter it is writing is a slow, silent narrowing, a closing of the sky, a long darkening that will eventually leave every island of stars alone in the black, ignorant of all the others. And so, we come back to where we began, to the claim in the title, and I think now you can see that it was not a trick of phrasing. Empty space was solved 60 years ago. That is, in a real and specific sense, true. The energy of the vacuum is right there in the equations of quantum field theory. It was computed. It has been computable for the better part of a century. The mathematics that gives the most accurate predictions human beings have ever made, the mathematics behind every transistor and every laser, contains within it an answer to the question, what is the energy of empty space? Physics did not fail to find the answer. Physics found the answer, looked hard at the answer, decided the answer was unusable and erased it. The answer was erased from the books, and the universe has spent every moment since then quietly insisting on it, writing it across the sky in the recession of the galaxies, refusing to let the deletion stand. What is left is the honest shape of our ignorance, and I want to give it to you plainly, because you have earned a clear ending rather than a falsely tidy one. We have 2 theories. Quantum field theory, which tells us empty space must be full of energy, and general relativity, which tells us all of that energy must gravitate. Both theories are confirmed. Both are among the most precisely tested ideas in the history of science. And when you ask them, together, the simplest question there is, what is the energy of empty space and why is there so little of it? They give an answer that is wrong by somewhere between 55 and 120 orders of magnitude. 2 magnificent theories, both true, that cannot both be telling the whole truth about nothing. Maybe there is a cancellation we have not found, some hidden symmetry, that trims the catastrophe down to a whisper. Maybe the vacuum energy does not gravitate the way all other energy does, which would mean a crack in general relativity itself. Maybe the value is an accident, small in our universe simply because observers can only ever find themselves in the rare regions where it is small. Maybe dark energy is not the vacuum energy at all, but some other thing, some field that changes over time, and the whole grand comparison has been a category error from the start. Each of these costs something. Each of them asks us to give up a piece of something we currently believe is bedrock, and not one of them has been confirmed. Let me give you a little more texture on those possibilities, because each one is its own quiet drama. The hidden symmetry idea is the one physicists have most wanted to be true. The most famous version is called supersymmetry, the proposal that every known particle has an undiscovered partner, and that the partner's contributions to the vacuum energy, would cancel the known particles' contributions almost perfectly, like a vast set of weights balanced against each other so precisely that the scale reads nearly zero. It is a beautiful idea. The trouble is that the world's largest particle collider has spent years hunting for those partner particles and has not found them, and a symmetry that perfect would have shown itself by now. The balance, if it exists, is spoiled, and the catastrophe leaks back in. The accident idea is the multiverse, and it is the one that unsettles people the most, because it is, in a sense, a surrender. It says, stop trying to derive the value of the vacuum energy, because there is nothing to derive. If reality contains a vast number of regions, or a vast number of universes, each with its own random value of the vacuum energy, then almost all of them are the crushed, sterile, galaxy-free disasters that Pauli's calculation describes. And in those, there is no one to notice. Observers, living things, minds, can only ever arise in the rare, freakish regions where the vacuum energy happened to land small enough for galaxies and stars and chemistry. So we measure a tiny value, not because any law made it tiny, but because a tiny value is the only kind of place a measurer could exist. A physicist named Steven Weinberg used exactly this reasoning, back in 1987, to predict, before the supernova measurements, that the cosmological constant would turn out small but not quite zero. He was right, and nobody is sure whether being right that way counts as an explanation or as the elegant abandonment of the search for one. And then there is the possibility that quietly rewrites the whole problem, that dark energy is not the constant energy of the vacuum at all, but a dynamical thing, a field spread through space whose strength shifts slowly over the lifetime of the universe. Physicists call this idea quintessence, and it is not idle speculation. Recent surveys mapping the expansion across cosmic time have produced the first faint hints that dark energy strength may not be perfectly constant after all, that it may be drifting. If those hints harden into a result, the consequences are enormous, because a dark energy that changes can do things a true constant cannot. If it weakens over time, the far future is gentler, less isolated, the closing of the sky slower than the worst case. And if it strengthens, if it grows into what physicists call the phantom regime, then the runaway does not stop at pulling the galaxies apart. It comes for everything. It would, in the end, tear apart galaxies, then solar systems, then planets, then atoms themselves, in a finite time, in a violent unravelling that has a name, the Big Rip. We do not know which of these we live in. The same uncertainty that hides the origin of the vacuum energy also hides the manner of the world's ending. I find that I do not experience this as a frustration. I experience it as a kind of awe, and I hope, by the end of these 2 hours, you do too. Because here is the situation, the true situation, laid bare. The most successful theory in the history of science contains, in plain sight, an answer to one of the deepest questions a mind can ask. That answer was too strange to use, and so it was set aside, struck out, quietly removed from the story we tell ourselves. And the universe, vast and patient and utterly indifferent to our discomfort, has been answering the question anyway, in its own language, on its own time scale, by slowly and silently pulling the galaxies apart. Empty space was solved 60 years ago. The answer was erased from the books, and somewhere in the smooth, humming, restless energy of the nothing all around you, the nothing inside every atom of you, the nothing stretching out between the stars, the real answer is still written, still waiting, still true. We just decided for 60 years not to read it. The universe never stopped.